topic named Sturm Liouville theory.
Thank you. Hi. Hi.
Eigenvalues and eigenfunctions. So basically, for the problem about finding psi of x with maybe let us call it lambda, let us call it psi n of x equals to lambda psi n of x. So it's an eigenfunction of this operator, and this is the eigenvalue. There are many questions after the previous lecture, or can we just continue? So, if not, let's continue. So, we proved several properties of this operator and of its eigenvalues and eigenfunctions, and today we will prove so. But first let us recall one of its properties, and then there was some condition on this P on Q on W that I will not repeat, but basically W and P are positive and P can vanish at the end of the interval. This x lives in the interval from A to B. So the property that is important today is the following: that first this maybe let's combine several properties. If you consider such an object, let us call this U of psi. For this object, let's call it phi, so that don't confuse it with the eigenfunction over phi is bounded by some number. So it's bounded from below. This follows from if this variation on phi. So, and since it is bounded from below, you can try to find the minimum of this functional. So, it is a variational problem, minimum of E. Well, we should say that a variation of E of phi or in other words, a d d epsilon of E of phi plus epsilon delta phi should be 0 phi and delta phi. And now let us compute this variation. So we need to have phi is a pair in this formula, so we will have 4 terms. How is it better? Maybe let's write it by a definition. So I'm just expanding first order in epsilon. Well, now let's expand this expression as a code. So maybe well, let's do it in steps. So there is this original expression. L to the second position. And now let us collect all the terms that contain delta phi. Let us try to express it as a scalar product of something with delta phi. So this can be written as 1 over phi delta phi scalar product with phi minus this expression. So we can do this for pure imagine and pure linear delta phi, and since it holds for arbitrary delta phi, then vanishing of this condition for arbitrary delta phi implies that this expression should be 0. So this should equal to 0 for arbitrary delta phi. So therefore, we should have that L phi minus phi L phi over phi equals to 0. So, but let us look at this expression carefully. This is a number. So we see that L times phi is proportional to phi times some number. So this phi is precisely the eigenfunction of A. L phi equals to lambda phi. And since we are looking for minimum, and if you substitute it here, then what will this expression equal to? Is it consistent or not? What would you say?
I'm sorry, what is the question?
So found that if you suppose that it is some number well, it is some number, but I suppose this number lambda. We see that phi should satisfy this eigenvalue equation. But then the question is it consistent with the equation itself? Because will this number actually equal to lambda?
Yes, because L phi will be equal to lambda phi. Lambda goes out, and then the two scalar product cancel out.
Yeah, thanks. So yes, it is a way to formulate this eigenvalue problem like this without specifying that there is some lambda. So solution of this equation gives us this lambda. So we can identify this phi with the first eigenfunction. So we can say that this the delta E of psi 1 variation of E of psi 1 equals to 0. Well, that's better to say that well, in principle, this equation has solutions for all eigenfunctions. This phi can be any of the psi-n's. But since we are looking for the minimum of this functional, then it is then this lambda is lambda 1 and phi is psi 1. So the value of this function is lambda 1. So this will find the first eigenfunction. But now let us ask the following question. What if we restrict this functional to the complement of to orthogonal complement of psi 1? So to answer this, let's first ask, is it true that orthogonal complement to psi 1 is invariant under the action of L? So the answer is yes, and we can prove it now. Let's call it let's call this orthogonal complement W1, which is say 1 orthogonal, which is a set of all vectors such that the scalar product of psi 1 with phi is 0. So it's an infinite dimensional space with this condition. So suppose that phi is in W1. Then let us check this orthogonality condition for L phi. position on the scalar product. So this equals to lambda 1 psi 1, which is lambda 1 psi 1 times pi, which is 0. Because phi was from this orthogonal complement. Maybe let us use this notation, because it's a kind of orthogonal complement in first vectors. So it equals to 0. The end of the book. So phi is in W1 orthogonal. So, since this is true, we can now try to do the same procedure with W1. So we can try to find the next eigenfunction and eigenvalue looking for a minimum dysfunctional on the orthogonal complement. Over phi's in W1 orthogonal. So this will give us another eigenfunction and another eigenvalue. Number 2 and psi 2. Once we do this, we can again now take orthogonal complement to first two eigenfunctions, and in general, when we find n of them, we can take orthogonal complement to the first n eigenfunctions. So, that is defined in Wn. Orthogonal is an orthogonal complement to span of psi 1 and so on, psi n. And since we are finding these eigenfunctions by minimizing this another functional, we know that any function that belongs to this orthogonal complement will lead to the value of energy higher than lambda n. So we have this by construction. And this assumption is that these eigenvalues go to infinity. In a sense, if we send n to infinity, we can get arbitrary high eigenvalues. So let us assume it now and then prove. And let us check that under this assumption, eigenfunctions of this operator form a complete basis in two functions on the interval. Namely, we need to prove that if we define projections of any function from there to this eigenfunctions, like this. So if we define such coefficients, then norm squared in a sense a square product with itself of this function minus sum from n equals to 1 to n, cn, cn. Equals to 0. If you take all of these eigenfunctions and try to maybe expand any other function of this basis, then this expansion will convert to the original function in this L2 norm. Norm of phi is by definition just phi times phi. Do you have any questions about this theorem?
that there are infinite eigenfunction and eigenvalue, or the fact that they are infinite comes from something that we already said?
It follows, but we have not proved it yet. So in principle, this applies to any operator or this speculations. In a sense, I could take a unitary operator for which all these eigenvalues would lie on the unit circle. Now, maybe it's a bad example. You take 1 over L. So the eigenvalues would be bounded. So this follows from the form of this operator, and this has to be studied, but we will do this a bit later. So for now you can say that in examples that you already know, it is true, because if it is the interval with simply second derivative, then its eigenvalue is called like n squared. If it is this Legendre equation, they also grow like n squared. And it's actually almost a general phenomenon, in the sense this behavior of eigenvalues at infinity follows from the behavior for second derivative. Well, this asymptotics is always more or less the same. So this has to be studied.
Thank you.
But if it is true, we can prove this. And we are going to do this now. So let us denote this vector by phi n. Let us study the following expression. So this phi n lies in W n orthogonal. And because we have explicitly structured all projections to lower vectors. So phi n is in Wn orthogonal. So it's actually easy to check, because the explicit form of this phi n is phi minus sum of maybe phi psi n or sin phi, maybe phi psi n. Phi n. So we take scalar product plus psi k. There is only one term in this sum. There is only one term in the sum of k is from 1 to n. There is only one term in the sum, and that has no trivial scalar product with psi k, and this is term corresponding to psi k. And precisely the same term will appear when you compute a scalar product of say k is phi n. So this is 0. And the structure is phi n. So this is indeed in this orthogonal complement. So now we consider this scalar product, and on one side we know that this scalar product is greater than lambda n norm of phi n, because it is true for any vector there. But on the other side, we can write this by definition. So we can write that it equals to phi minus sum of Cn psi n. So it is phi of phi, first term, and other three terms will be the same because they will be the same because all of them contain psi n that will be projected onto phi. So we can write as
scalar product phi with L of the sum we don't have.
Okay, let's write this explicitly. So we have so let's first just rewrite what we already have. This first on this term, when we take and then L5. Then minus symmetric draw. This string sounds. But now let's start transforming this. So in this term, we can move L to the first part, as saying that epsilons are its eigenfunctions. We can do the same here, but here it overlaps by eigenvalue. So we have this. Then in this sum, each psi multiplied by phi will give psi times phi. And the same but with exchange order. So this will equal to sum over n, gamma n, phi psi n, psi n, or psi n psi n. Second term is the same. And the last term, so in principle it contains two sums, but this psi's are mutually orthogonal. So we'll have only one sum surviving. Actually, probably this guy will be conjugated. So it will give the same kind of expression. Group plus n phi psi n phi or n psi. So we can cancel these two sums. We are left with this expression. So since we have already shifted our operator so that its eigenvalues are positive, we know that this term is positive. So we can say probably I can erase everything except the operator. look at the first and then the last term in this equalities slash inequalities. So we know that pi minus the sum is greater than lambda times phi n phi n. But since it is positive, we can say that it is strictly less than simply phi L phi, which is a number that does not depend on n. This norm is less than 1 lambda n phi L phi. And since lambda n goes to infinity, this goes to 0. The end of proof. Are there any questions about this part? Oh, just some kind of cake which can also be found in the world's lecture notes as in this form. Okay, but before this, we made an assumption that we should have infinitely many eigenfunctions and eigenvalues, and that these eigenvalues go to infinity when we send n to infinity. And now we prove this. And to do this, we can use all these statements about numbers of zeros of solutions. So let us draw some pictures. Okay. Let's say that we are studying some equation with zero boundary conditions. For simplicity. It also applies for other boundary conditions. It will just change the counting of zeros a little bit. So, how do all these eigenfunctions look like? Okay. We have the first eigenfunction, which has just two zeros in A and B. So we probably do not prove that probably we need to prove that the lowest eigenfunction has no zeros except the boundaries. But let's assume that it is true. It does not affect all other parts of all this argument. So there is this eigenfunction. Our comparison theorem said that if we consider the eigenfunctions for higher energy, like if we consider any solution of this equation with higher energy, it will have a zero between the zeros of this solution. In particular, the next eigenfunction should have zero in between. And let us ask even more general question. How does transition between psi 1 and psi 2 look like? So there was this eigenfunction, and at the end have eigenfunction psi 2 that has 1 zero and 3 b. And we know that actually any function that corresponds to an intermediate energy that will have 1 zero in this interval. So it's more or less clear that this zero should should enter either from the left or from the right. And, in principle, this equation has two independent solutions. But for our purposes, let us fix one boundary condition of the solution, saying that psi psi of x and lambda such that it vanishes at a. So if one value is fixed, then the only option for the zero is to appear on the right. So this picture will look like this. So, small variation of energy will turn this solution of our equation into something of this form. This is lambda equals lambda 1. This function is psi of a lambda. Also, so psi of x lambda. And this is drawn for lambda greater than lambda 1. And this picture is for this picture is for lambda equals to lambda 2. So we see that first eigenfunctions of our operator, eigenfunctions and eigenvalues, eigenvalues of our operator can be found as the zeros of the equation psi of a lambda psi of b lambda equals to 0. take the solution that vanishes on one boundary, you need to solve this equation for other boundary. So it's first general observation. Second observation is that if you have two values of lambda such that psi of one value of lambda has such that psi has different number of rows for these lambdas, then this equation has solutions on the interval between lambda, let us write this image please. Maybe I should have used this. So if it is true, then this Liouville equation has rules between lambda prime and lambda 2 primes. And the last observation is the following: that we have we have solutions to this equation with arbitrary number of rows. And arbitrary lambda. This is the first. We can simply consider we can simply restrict. Well, actually, I will prove this only for P and W equals to 1. but it is true in general. We can compare the solution of this equation for can compare this operator the solution of this equation. Was like this. So we know that the energy, the eigenvalue corresponding to this function is bigger than the eigenvalue corresponding to this function. But this function is explicitly known. This function is a sine function. It has zero, such x equals to a plus can you actually tell what its zeros are? What is the formula for all zeros of this function?
N times pi plus a.
No, there is this aspect. So it is sin equals to a plus n over the square root. So if we send lambda to infinity, the distance between these zeros decreases, and we have the following picture. So maybe I can erase something like this. since we know about this covariant theorem, zeros of function with higher eigenvalue should actually I should have subtracted here. I should have subtracted here also minimum of Q. So yes, and that there should be some well, this epsilon contains a minimum of Q in itself. So there should be a restriction that lambda is greater than lambda minus epsilon minus minimum of Q. Yeah, but the picture is the following: that there are zeros of this psi tilde, and the zeros of psi are in between them. So there is at least 1 zero in each interval. Like it can be actually more. So, in this way, you can construct solutions to this equation with arbitrarily high energy eigenvalue with arbitrary number of zeros, and so you can indeed obtain eigenfunction with arbitrarily high lambda. And it's kind of the end of proof that it's not very close. Do you have any questions about this? Yeah, also you may see that this restriction that zeros of n eigenfunction should fit between zeros of some sine function tells us that the general asymptotics of these solutions for high lambdas will be described by trigonometric functions. And it is more or less clear because if you take such an equation and send lambda to infinity, then, like in this equation, if you send lambda to infinity, then this term will be dominated by this constant. And you know, asymptotics is more or less trigonometric. So maybe it's all about general theory. The main result is the following. If we manage to solve this second order equation, in a sense, we are sure that we found all of its solutions with given boundary conditions, then we can take these functions and use as a kind of analog of Fourier transform. So, in particular, we can take the result of polynomials as two bases in functions on the interval from -1 to 1. And but there are other examples. And let's.
Is this also related to Chebyshev polynomials that can be used as?
Yes, there are also examples of this.
Okay.
So Chebyshev polynomials are more or less cosine and sine functions written in a different coordinate.
Okay.
So this is the reason why they are orthogonal, but it's an explanation. But they can be interpreted operator differential. And maybe instead of considering other examples, I propose to look more carefully at this case of polynomials, namely to see how the solution of this equation would look like. So, let's start with this polynomial span x. Do you remember the differential equation they solved?
With the Sturm Liouville operator?
Yes. If I write it in this x coordinate.
1 over negative 1 over w of x?
No, there are some specific values. So we had this Laplacian theta phi for n equals to 0, and this Laplacian looks like 1 over sine of theta being the theta sine of theta being the theta. So if you write it in its coordinate, this becomes the sine theta sine square theta dv sine theta, which is dx 1 squared dx. So this polynomials should satisfy the eigenvalue equation minus dx. Let me write it like this. With lambda n's given by n and n plus 1. So in particular, I have P0, P1, P1 equals to x, and so on. So equals to x squared minus 1 over 2, and so on. I will go to ask the first question. So we have this second order differential equation, and we know its solutions. But we have only we know only one solution for a given eigenvalue, and we have proved that if we respect this boundary conditions, then it should be the only solution. But in principle, this equation has another solution for the same eigenvalue. And do you have any idea how one could find the second solution, for example, for the first Liouville polynomial, for 0, so for the first Liouville polynomial? without solving this second order differential equation.
It's symmetric, right? No, it's symmetric.
Oh, the idea is the following, that you know that once kind of two solutions is times this function is constant.
I think if you put in negative x, you get the same. Never mind.
So if you have a second solution, then Wronskian of a good solution, which is a John polynomial, with this second solution should be constant divided by 1 minus x squared. So let us say that it is just 1 over minus x squared. And this is a first order equation. So that we can write this Wronskian even in a better form. We can write that Wronskian of f and g x equals to let me put tilde here. It equals to g squared of x times f over g prime. Is it clear? Well, it's simply this ratio as f prime g minus g prime f divided by g squared, and multiply by g squared and get Wronskian. So taking this into account, we can say that this equation turns into p n cubed over p n prime is equal to 1 over 1 minus x squared times p n squared of x. This can be integrated. We simply integrate the right hand side and get this APM tilde. So, any questions? So if you have one solution of OD, the second solution can be obtained simply by integration. Now let's apply this idea to Physio, just to see what happens with this function. 1 minus x squared, which is dx 1/2 of 1 minus x plus 1 over 1 plus x. So it was 1/2 times log of 1 plus x over 1 minus x. That's good. So you see that there is a function that has singularities at the ends of our interval. And we should compare it with another situation. So this function vanishes at boundaries at 0 and pi. And this function will not vanish. So you see this problem that in order to find the solution to this equation, we should study its asymptotics at x equals 1 and minus 1. So in particular, we can study solutions that are regular at 1 and see what happens at minus 1, or vice versa. But there is also another option, maybe a simpler one, because this equation is symmetric. We can study solutions that are even and odd at the origin, because we know that since this equation is asymmetric with x minus x, all its values should also be asymmetric. And then we can look for solutions that are regular at 1 and minus 1. So let us try to find the eigenvalues of this operator algorithmically without all this tricks with dimensional potentials. We have this equation, and we want to find its solution that is regular at the origin. Well, all of its solutions will be regular at the origin. We simply say that we can expand it as a Taylor series at the origin. So we want to solve this equation, minus is some from n equals 0 to infinity. Cn Cn x n. There is some Taylor series in the origin. Let's simply substitute here. Maybe before that, it's better to write the separator a little bit. Like this. The first term. So we get in series. They're in this formula.
Sorry?
Do I agree with this formula?
Yes.
So we can actually shift the sum to n equals to 2 because the first two terms vanish. So we could actually shift the sum as well, but we can't do this now. So now we can shift the summation index in this term so that this x to the power n minus 2 becomes x to the n, and keep other sums the same. So what we're working at. So we get Cn plus 2 n plus 1 times n x to the n. And now this n goes from 0 to infinity. So now we can collect all the terms in front of x to the n and say that if this quality holds, then it should hold in each order of n. So we have the following equation. C n plus 2 times n plus 1 times n plus n plus 2 Cn. 7 n minus 1.
Sorry, the second term of the equation doesn't start, the second summation doesn't start from 2.
Where?
Yes.
But it doesn't matter. It's first terms. It's first two terms range anyway. So we can write down the
Okay. Of course.
plus minus lambda. Equals to 0. So we have the following regards evaluation. Cn plus 2 equals to Cn times minus equals to 6n n plus 1 minus lambda over n plus 1. So now we have two options. Any questions? Option 1 is lambda generic. Then this recurrence can be solved in terms of gamma functions, but it's not really needed. We can simply say that Cn is of order 1 plus O of 1 over squared, something of this kind. I think. Maybe no, plus order of 1 over n. Which means that what is the radius of convergence of such series?
1.
Yes. And actually, you can check symbolics also tells us that it's not only some singularity on the unit circle, it also produces singularity at points 1 and minus 1, because there are no fails in this symbolics. So the rule of singularity is at plus minus 1. So this is more or less what we saw here. There are solutions that have a logarithmic or some other singularities at the boundary. it's not a solution of our spectral problem. And if you want it to be a solution, we need to adjust the lambda such that this current terminates at some point. And so it will terminate this currents for ends of the same parity as lambda, because this currents shifts the index by so n should have the same parity as k. Minus k squared minus k. Why do this? Because in principle we can solve this accounts. Even some tutorials in our functions. It can be written as Cn and plus k minus k. Minus k. So probably not this recurrence, but you see that in principle you can write each Cn as a product of some numbers that are shifted by 2. So in principle there should be an explicit formula for Cn equal to a ratio of some factorials or double factorials. And of course you see that they are polynomials since this recurrence terminates at n equals to k. And you also see this eigenvalue. So what we have done actually that we proved that all those polynomials that we obtained from the three-dimensional potential are all solutions of this equation. So they form the basis in the space of functions on this interval. So we obtained that all the values of this equation have this form, k plus 1. So it was not just a subset of eigenfunctions. And this technology is pretty general. So when you start from some second order differential equation, you can simply try to find its solution as a series, then try to find coefficients of the series in some explicit form, and then so in some cases you can study this termination conditions. Or there are other cases when you will be interested in zeros of this function. So in that case, you will not have explicit formulas, but you will be able to transform this series formula into some integral representation using some tricks. This idea usually works in this or in that form. Other examples which we will study later are related to the ideal component of Laplace or the wave equation. So those operators also have this form. So we have in 2D case our Laplace sum looks like this. And also the angular distribution for given eigenvalue. Some squared over r squared, and so on. And there is so this operators, I can probably put minus signs here. So this operators also have Sturm Liouville form with P equal to R, W equal to R, and the potential Q equal to squared over R squared. In this case, those are R squares, and this term is all the same. So we'll start next time, and this will correspond to these two functions. You see that the setting is absolutely the same. There is only different functions. Also, organizational announcement. I wrote this, but just to remind you, next week I will not be in Trieste, so next two lectures will be on 16th and 17th of December. Do you have any questions about this?
Did we decide in February when we'll do the exam?
But this will be up to you. So when I know my restrictions, like which days are appropriate